Okay, testing 1 2 3. One more test. One more test. Alright, cool, that's great. It's been a while. I went on holiday, so that's why I haven't done it for quite a while. And I've been on holiday trying to think about the kinds of differentiation I might be able to use for my machine learning models, but very, very high level, just guesses and kind of testing my mathematical knowledge. And I found some gaps. So although I think although I thought I was using integrals correctly, I think I might not be. So I need to learn some kind of fundamental parts of mathematics to kind of push forward with that. And just in a couple of pubs, I was wondering um, what exactly happens when proteins fold. Like what is the actual mechanisms behind it? Now I know like intuitively that there are forces like the hydrogen bonding and like hydrophobic mechanisms and even maybe hints of strong and weak forces. But still, I think I need to work back through the history of things like how do they know about electrons and how they know about the positional parts of an atom. And I think given such a kind of underlying understanding that I'd get from that, I'd start to be able to intuit some of the things that kind of AlphaFold are dealing with, or DeepMind with their machine learning models. So I'm going to start with Duolingo because I haven't done that for a while, and then I'm going to try and push through just a little bit this evening, try and find a kind of path to understand more about the underlying mechanisms of atoms. And I think this will be helpful because then I can start to, yeah, intuit the folding mechanisms behind proteins. So starting with this, yeah. Right. Okay. So, oh wow, we'll do test 2 sessions then. So let's practice this. V, Ro, V. Select the correct characters for V. V. Ro. Select the correct characters for Ro. Ro. Me. Me is this one. Select the characters for me. This one. The vase is pink. Keyboard. Greek. The vase. To. Vaso. Rose. I think. Something like that. Oh, I'm not even typing. Haha. To. Vaso. Rose. Rose. Let's have a look. Ah, so it's this Z thing. I think I did know that. I even reached for it, then I thought this is the S on the keyboard, so and Vaso. Okay, that's great. And we're missing this accent here. Ooh. How do I do accents? Okay, apparently I don't know that. Maybe it's graphic. Graphic? No. Function? No. I don't know. Okay, we'll just go with Vaso. To Vaso Ah, okay. Ine rosa. Ine is. Ine rosa. Okay.
Το αβοκάντο είναι ροζ.
To
Το αβοκάντο είναι ροζ.
avocado. To avocado.
Το αβοκάντο είναι ροζ.
Ine rose. The avocado is pink. Ah, av. Yeah, I didn't know that. Silly me. Cado. This is interesting with the N, isn't it? Yes. Kai? Okay. Nai. To. Rosa. Vase. Vaso. Okay. Ne? Oh, with. Okay, yeah, that's fine. That's a capital. Ne? To. Rosa. Vaso.
Το βάζο είναι ροζ.
To. Vaso. Είναι rosa. This has another letter. Rosa. This is wrong. Oh, it is right. Okay. To vaso. Είναι rosa. It's water. So, είναι. Okay. Είναι nero. Che. Oops. Che. Carotto. One T. Okay. Or one do. Είναι nero. Che carotto.
Το
Okay.
ρύζι είναι ροζ.
To resi. Ri. Risi. Something like that.
Το ρύζι είναι ροζ.
Είναι rose. This one is wrong.
Το ρύζι είναι ροζ. Το ρύζι
Risi.
είναι ροζ.
Ri. Okay. I remember this one. Yeah. It's water. Είναι nero. Avocado. Avocado. Oh, I've done it again. Avocado. To avocado. Είναι rose. And
Είναι νερό.
is. Write this in English. Hey, hey, hey. Okay. Is water. Oh, it's water. It is water, I think. And maybe it's missing a apostrophe there. It's water. Or it's water. Maybe it is that. Okay. The pink to. Rose. Mini market. The vase to. Vaso. Είναι rose. The vase. Yes, that's right.
Το αβοκάντο είναι ροζ.
To avocado. Είναι rose. Avocado. To. Okay. We won't do another one because it's long. Good to remind myself of how that works though. Okay, cool. So let's go back to English. Great. Boom. Done. How big are we looking here? Let's see. Oh gosh, I hope that's a higher resolution than that. It is. Okay. Right. This is not what I want to look at. So I guess episode 15. Episode 14, I think was. Um, Funnily enough, I don't really remember writing that, but this looks like um, some kind of comparison from input. Yeah, okay, inputs and desired outputs. Uh, this is talking about the weighting is equal to activation layers, but then we're talking about a change in, what is this? Whatever this is, energy. Um, as a function of x and angle over time. So this is to do, okay, so this is trying to figure out the angle between two the input and the output, I guess, or maybe just the outputs of the input. I don't remember doing that here, so maybe I did this another time. Okay, what's 13 got in it? Oh wow, okay, was I doing this? I didn't know I was doing this online. That's cool. So this is the ML stuff I'm trying to figure out, and then some. What is this? Interesting. Oh yeah, okay, the paper on the. Okay, I remember all this stuff. Cool, and then thinking about the bigger picture. Yes, 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 yes. Okay, completely irrelevant for now. Right. So, really back to basics again. I want to know. I suppose a couple of things. I'm going to start with if I have an atom and it's covalent. So let's say we've got well, uh, that's a terrible drawing. Let's say we've got oxygen, and we're going to bind to, I don't know, uh, yeah, hydrogen. Then this is in a covalent manner. Then I want to know how to determine the positions of the energy or the kind of energy positions of the electrons um, that are shared between the bond. I want to know how to determine the position because I know that you've got the S is the middle, the P is the second one, and you've got D, and I think it's F. So this is 2, 6, something like that. Something in 14. I can't remember. Something like that. Maybe it was 2, 2 and 2 and 6. Maybe it was 2, 2 and 8. Anyway, so this kind of structure, I need to understand this more because I think then I'll get some physical models or physics calculations I can make for specific layouts. Using things like maybe Maxwell's equation. I don't know. Just a complete guess there. You're probably laughing now. So let's see. What's Maxwell's equation? I can't remember. Maxwell's equation. I think it's like particles or so a couple different equations. Electromagnetism. Yeah. Okay. Yeah, that could be about right. So yeah, this is what I'm going to work on. So step one. No, let's undo that. Step one is back to the periodic table. Let's learn about this shit again. Right. So this one has an atomic mass of 1. It has no description of its. Oh yeah, it has. Yeah, 1s1. So this is. Yeah, okay. So the electron configuration. I can't hold it open. If I just click it, maybe get rid of this shit. Where is that S again? electron configuration. Here it is, 1s1. So I need to know what that actually means, right? Let's just click this. This looks interesting. Thanks. Okay. Right. Let's take a picky of that for hydrogen. So if I was to draw this, how to draw electron configuration. Writing and drawing electron configuration. Let's see what they mean. Yeah, GCSE, of course. It's the only way. Scientists' ideas about atoms have changed over time. Today, they agree that atoms have a positively charged nucleus made of protons and neutrons, and negatively charged electrons that orbit the nucleus in shells. Writing and drawing electron configuration. Take sodium as an example. Sodium has 11 electrons. Sodium has 11 electrons. Let's just go and confirm this so I understand it. Sodium is Na. So, okay, so the atomic mass 11, and this is because electrons heaviest generally orbit atomic nuclei in distinct shells, but calculations show the outer electrons of organosome, the heaviest element found, so the heaviest part of atom. Neutron decays indicates formation of proton, electron. Proton doesn't give that, so we can neutron is heavier than proton. Mass of a neutron, proton, electron. Neutron is the heaviest out of the 3 subatomic particles. And that, if I remember correctly, was... So if sodium has 11 electrons, that is the same as the... That is the same as the... So we've got hydrogen, and there is... No, so we've got, sorry, Na. Let's just go over here for a second. So we've got Na. Can you see that? Yeah. And this has 11 electrons. So forgetting the configuration, that's 1, 2, 3, 5, 6, 7, 8, 9, 10, 11. And that means it's got 11 protons. These are negatives. And then you've got, yeah, let me just delete this shit. 1, 2, 3, 11. And that means you've also got, so I think it's, shit, I can't remember, damn it. This is so annoying. Okay, so an atom. GCSE bite size. Let's figure this out again. I just can't remember. Maybe it's in my documents here. What we found out. Nope. Notes. Yep. Probably worth remembering. So 4. Nope. Oh yeah, we got into it here. Condensed formula. 6 protons equals atomic number. Protons are the positives. Electrons. Count of electrons must be equal to count of protons. Otherwise, the imbalance would cause the element to change to another element. So electrons and protons are balanced. So the atomic mass. Oh, the atomic number. Yeah, you see, periodic table, numbers explained. So I think, yeah, this is the atomic number, not the atomic mass. The atomic mass is, well, let's go into it. It probably says it. Mass. Relative atomic mass is 1008. Ah, okay, that makes a lot of sense. Cool. So the 11 in the Na Yes, it's 11 electrons. That means it's got 11 protons. So let's go back here. Let's draw this a bit better. So Na better, draw it better, equals 11 electrons and 11 protons, and neutrons is going to be how to work out number of neutrons. Neutrons. Let's see, what can I just tell you? All that guff. Locate the electron on the locate the element on the periodic table. For this example, look at osmium OS, which is in the 6th row down. Great. Find the element's atomic number. So this is going to be 76. OS is number 76, meaning one atom of osmium has 76 protons. The proton number never changes in an element. It's basically what makes that element that element. Great. Element's atomic weight. The number is usually found beneath the atomic symbol. Note that the chart in this example is based solely on atomic number and doesn't list atomic weight. This won't always usually be the case. Osmium has an atomic weight of 190.23. So its atomic mass is 190.23. Round off the atomic weight to the nearest whole number to find the atomic mass. Round off the atomic weight to the nearest whole number. The atomic weight is an average of the isotopes of the elements. That's why it's not usually a whole number. And so then it's atomic weight minus the number of protons. Oh, no, that's interesting. So, wait. That means that Na, let's go back to Na. What is its mass? It's 22.990. Did it say be rounded to 190? Okay, well let's not round it. What happens then? So if you go 22.90, is that sodium? Yep. And then it was, what was it? Round atomic weight. Atomic weight take away protons. Atomic weight take away 11 equals 10.1. Wait. Sorry. 22.9 take away 11. Yeah, okay. I was like, that can't be right. 22.9 take away 11. 11.9. So that means that the neutron number of neutrons. That means that is the number of neutrons. 11.9. Now I suppose you can't have a 0.9 of a neutron, so I guess it's going to be 12. Let's find out. Neutrons. How many neutrons in sodium? 12 neutrons, alright. Interesting. So this is, yeah, the ceiling of 11.9. Okay. Yeah, I didn't actually. That is definitely going to be 12, isn't it? Because you can't have points. Awesome. Okay. So I do kind of remember it. Right. So with hydrogen, we've got. Let's just do it a second time. We'll do it one more time after that. Oh, we'll do it a couple more times, so I can remember it. So this is hydrogen has one atomic number. It's got 1.008. 1.008 is its atomic mass. This is given for M. And then thus the mass take away of 1 is going to be equal to 0.008, which ceiling is going to be the neutrons equals 1, and that means the atoms, the electrons are going to be 1, and the protons are going to be 1. So let's just double check that. How many protons in hydrogen? 1. How many neutrons in hydrogen? Has no neutron. Ah, yes, of course, because it's rounded down. Okay, my apologies. That makes complete sense. Yes, that makes a lot of sense. Okay, so it's rounded to nearest. Okay, that makes sense. And then so we'll go electrons 1. Okay, let's do another one. Let's do Ti titanium. Okay, titanium has 47,867, 47,867, 47,867. It has titanium is 22. So 22 minus is going to be let's just calculate it. 47.867, take away 22, 25.867, 25.867, it's closest to that, so we're going to ceiling it, and that equals its neutrons. Then its protons and electrons are going to be equal to 22. Let's just double check that, so it's going to be equal to 26. Neutrons in titanium. Hydrogen, and we've got this Na. And electrons in titanium is 10, 18, 22. Yep, okay. Tons, protons in titanium is 22, and neutrons is 26. Okay, right, we understand that. Okay, that's fine. Good stuff. Right, given that, let's continue. So take sodium as an example. Sodium has 11 electrons. It has 2 electrons in the first shell, 8 in the second, and 1 in the third shell. Ah, so I was wrong about this. Unless these can be on different parts, it's maybe an expression of the configuration rather than the ring. Okay, that might be it. So you can write sodium's electron configuration with numbers and commas. 2, 8, 1. The electron configuration of sodium can be shown in a diagram. The dots represent electrons. Electrons may be shown using dots or crosses. Right, okay, so let's figure out, so this was, what was this? Sodium again. So it's got a configuration, electron configuration is 3s1. I wonder if it's got anything else here. Let's have a look. And it said it could be written as, what was it again? .281. So if I go and search for 281. Doesn't say that. Okay. So that electron configuration, that S thing is important, so we've got to carry on. So let me just take a picture of this. How do I get down again? I can't remember. Panning? Oh yeah, that'll do it. So Na is this. Nice. Yep. Let's go to this. Atoms have a radius of about 0.1 nanometers, or 1 to the 10 1 part in 10 to the minus 10 meters. The nucleus of an atom is less than 1 to the 10,000 the size of an atom. Atoms have a radius of about 0.1 nanometers. Small world, isn't it? Or 1 part in 10 to the minus 10 meters. Yeah. The nucleus of an atom is less than 1/10,000th of the size of an atom. Yes. Isotopes are atoms of an element with the same atomic number, okay, but a different mass number. They have a different number of neutrons. Let me just skip ahead here. I want to make sure we've got positions as well. We don't. Well, given this is... do I continue? I guess so. Let's just continue. There might be some juicies in here. Yeah. Atoms have a radius of blah, 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 blah. Isotopes are atoms of an element. Isotopes, yes, we know what they are atoms of an element with the same atomic number but a different mass number. Same atomic number but a different mass number. So let's take... So this is same atomic number but different mass number. I don't know if that's described very well, in fairness. Close tabs to the right. Isotopes are atoms of an element, okay, with the same atomic number but a different mass number. That means you've got separate versions of that element, the isotopes of that element, but they'll have a different mass number. But they may have a different number of neutrons. So Ci, what is that, or Cl? Yeah. Let's take a look at this bad boy. Cl 35, 37, 17 atomic number. Oh, let's just replay this to get it in my head. So we've got Cl is going to be, what's its mass? 35.45, 35.45. Take away, it's got this 17. Let's get a whole meta on this. 35.45, take away 17. Equals 18.45, so that's going to be, nope, 18.45, and then we're going to have that as the neutrons and atoms and protons. Electrons and protons is 17. Okay, and then we've got what? Isotopes, there they are. Key isotopes. I wonder what key means in this. The key isotopes. So the most important? I guess so. 35 and 37. So if they're a different atomic number, so let's go 35 and 37. Let's see. No, okay. Okay, I see. It's just a different mass. What was the mass of the other one? 35. I see. Okay. So these are atomic masses. So it's still going to be... Let's move this up. Oh dear. How do I select that one? Yeah. So it's going to be minus 17, minus 17. So this will be 20.45. Oh gosh. One note. 24.5. Oh, this one here. And this will be, yeah, I mean, it's the same, right? So it's going to be 18. 18. So these are the differences. Okay. Chlorine exists. Oh, it's chlorine. I see. Yeah, I knew that. The table below shows the number of subatomic particles. Subatomic particles, that means they're inside the atom of the two isotope types of chlorine. So we've got number of neutrons, 18 and 20. Let's see. Yep, that's correct. And electrons. Yep, cool. Cool, 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 cool. Great. Got that one down. Is anyone watching? Anyone talking? No, okay, cool. Alright. Calculating relative atomic mass for elements. Most elements contain a mixture of isotopes. Okay. They contain a mixture of isotopes? Okay, interesting. Each present in a different amount. The term weighted mean mass takes into account the different contribution of each isotope to the overall mass. So let me just see this. If I were to do, what is it? 35 plus 37 divided by 2. No. Wait. You've lost them together, right? Yeah. God. Get average of equation for mean. Sum of the terms divided by the number of the terms. Yeah, I did that right. Okay. So this one is 52.5. Oh, haha, bod mass. Ta-da! 35. 35 plus. I knew it'd get me one day. 35 plus. Oh, you a son of a gun. 35 plus 37 divided by 2. I knew I'd do that. I knew I'd do that. Yeah, that is so funny. Fucking bod mass. So funny. Okay. So that's average is 36. Okay. So the mean is 36 across all isotopes. Oh, unless we need to include that one as well. Let's just include that too. So let's go back and do this. In fact, you know what? I think it's going to be easier to do Python here. Let's just do a bit of Python. Right. It's 35.45 plus 35 plus 37 divided by 2. Oh, divided by 3. You're an idiot. 35.816. 817. 35.817. Right. 35.817. Yep, okay. And if that's the case, then... Right, okay. So this says the mass number 1 times the abundance plus mass number 2 times the abundance divided by the total abundance. The term weighted mean mass takes into account the different contribution of each isotope to the overall mass. The contributions of all isotopes are combined to give the relative atomic mass, minus the weighted mean of the mass numbers. The contributions of all isotopes are combined to give the relative atomic mass, minus the weighted mean of the mass numbers. Relative atomic mass, minus. So let me try this. So it says the relative atomic combined to give the relative atomic mass takes into account the different contribution of each isotope to the overall mass. The contributions of all isotopes. Okay, relative atomic mass is not the same as mass number. Yeah, relative atomic mass. So what is this one? This is atomic mass, maybe, was it? Mass number. I see. Oh, I see. Oh, is it not? So this. So what the fuck is the mass number then? If it's different. Really? Atomic data sounds good. Infinity. Huh? Wait, what? This really does say that. It says. Oh, where's my where's it gone now? Did I close it? No, I didn't. Okay, this is a mass number, 35 and 37. And this one was what? Chlorine's mass was what? Doesn't say that's sodium. Chlorine's mass is mass of chlorine 35.453. 35.45. Okay, well. Atomic mass versus relative atomic mass. Relative and average atomic mass both describe properties of an element related to its different isotopes. However, relative atomic mass is a standardized number that's assumed to be correct under most circumstances, while average atomic mass is only true for a specific sample. Okay. Relative atomic mass is an average mass which takes into account all of the isotopes and their abundance. It is not always a whole number. However, on your data leaflet, apart from chlorine, the relative atomic masses have been rounded to whole numbers. So what is a abundance? I mean, I know what abundance is, but abundance, let's see. Oh, great. Nice new word you've put in there. Let's see if number 7 explains that. No, of course it doesn't. Okay, well, let's just take it as it is then. So I'm going to read it again. Most elements contain a mixture of isotopes. Most elements contain a mixture of isotopes. Okay, we know that because we can see that Cl has 35.45, it has 35, and it has 37. Cool. Each present in a different amount. Each present in a different amount. So let's just click through to this. Atoms which have the same number of yeah. Okay. So atoms of the same element, but they have a different number of neutrons, so they have a different mass number. The term weighted mean mass takes into account the different contribution of each isotope to the overall mass. The contributions of all isotopes are combined to give the relative atomic mass minus the weighted mean of the mass numbers. Abundance. So what is the output of this then? Divided by total abundance. So the mass number of 1, so let's say this is M1 is 35, M2 is yeah, okay, M2 is 37, so it's going to be M1 mass number 1. M1 is, so I don't actually think I've got So maybe it's that. Maybe it's always that. Is it measurements contain no this one? This one I think it says it. Isotopes are atoms of an element with the same atomic number but a different mass number. So if that's the case, then I need to know what the mass numbers are. Mass numbers for chlorine isotope. How to find mass of isotope. For any given isotope, the sum of the numbers of protons and neutrons in the nucleus is called the mass number. The sum of the number of protons and neutrons in the nucleus is called the mass number. This is because each proton and each neutron weigh one atomic mass unit. By adding together the number of protons and neutrons and multiplying by 1 AMU, you can calculate the mass of the atom. So adding together the number of protons and neutrons, then so the number of protons and neutrons is 17. So that's going to be is 34. So the mass is 34. This is the God. So we got okay. So let me get a new sheet. So 34. Let's defuck this. This is crazy. Right. Defuck this. Okie dokie. CL 34 plus 34 times 30. 35 and 37. 35 plus 34 times 37 divided by 35 plus 37. Alright, 35 plus 37, 72. And then 34 times 35, 1190. 34 times 37, 1258 plus 1190 divided by 72. 34. Holy shit. Yeah, okay, right. So 34 equals that. And that means the relative atomic mass of chlorine is not that. It is not that. Okay. Well, maybe I've taken, what is this? So what is 17 times 2? We did that, yeah. Huh. Ha ha ha. Abundance. Atom abundance. Isotope abundance. natural abundance of the stable nuclides. What is isotope abundance? In physics, natural abundance refers to the abundance of isotopes of a chemical element as naturally found on a planet. The relative atomic mass of these isotopes. So if I do abundance of chlorine 37, 25%. Chlorine naturally exists as two isotopes. The abundance of chlorine 35 is 75%, and 37 is 25. So 35% is 35 is equals 75, and then 37 equals 25%. Okay. So these are percentages, which that was not clear to me. So now this equation is different because it's going to be it's going to be 75 plus 25 divided by 100. Oh, I see. Oh, okay, that makes sense. That makes some sense. It took me a little while to realize that. 35 times 75. Let's see what comes out though. 2550. 34 times 25. 850 divided by 100 plus 2550 divided by 100. 34. Fuck. That's also not right. So how do you get this smaller number? Have these been rounded up or something? Relative atomic mass of chlorine. Yeah. Did I round something up? Accurate. Oh, where is this from? I wonder. This is coming from here, alright. Atomic weights. Yeah, okay. But they are 35. No, okay, I see. That's correct. Oh no, why am I getting this different number? How does anyone at GCSE figure this out? Holy shit. Okay. Let's just read it again, I guess. Atoms have a radius of about that. I mean, is this necessary to know, or is this just an interesting fact? I don't know. So the nucleus of an atom is less than 1/10,000th. Isotopes are atoms of an element with the same atomic number. So okay. So let's take these ones again. So this is going to be atomic number is 17. Wait, let's just double check that. Cl. Where are you? Yep. Cl. Ha. Cl has atomic number. Oh. Weird. Thanks. Oh my god, what the hell is this? Right, let's try that again. God. Cl atomic number is 17. Okay, fact number 1. We have, let's go into here. It's 35.45, so 35.45, so it's atomic mass is 35.45. Okay. So now, well, okay, that's interesting. So let me just go and get that other picture again. This one says 35.45. 35.446, 35.457. That is so interesting. Where the hell did this come from? What is this one? Yeah, because that's 35 and 37. Nice to see the abundance there, though. Oh, hang on. This was talking about... don't lose track. Okay, cool. So we know this. So 35.45 is coming from... This says 35.5. Oh, look, though. Yeah, okay. So it is so the relative atomic mass is being used in this equation. So the relative atomic mass, whatever this means, as a function of the atomic relative. Oh, okay. I see. So this is what they're calling it. AR, the atomic relative atomic mass is equal to the mass number, and it says mass numbers are whole numbers because they are the number of proteins plus the number of neutrons. Okay. And then it says relative atomic mass is an average mass, which takes into account all of the isotopes and their abundance. It is not always a whole number. However, on your data leaflet, apart from chlorine, the relative atomic masses have been rounded to whole numbers. And this says, or somewhere it says, somewhere it said that. This one? Nope. Relative atomic mass is not the same as mass number. Relative atomic mass is not the same as mass number. Mass number refers to, because this one's saying 35 and 37. So we've got this 75, and then 25, plus, and then divided by, well, 100. Thirty-five times 75, 2625, plus 37 times 25, 925. 95, 925 plus 2625 divided by 100 is 35.5. Yeah, okay. So this abundance, but this abundance seems way too precise here as well. But that's weird. Mass number, if that's not the same as the relative atomic mass, and yet this one's mass number is 35, oh, I see. Now hang on. I wonder if it's the relative. I wonder if it's because it's been rounded already, whereas yeah, the relative is the mean. Huh? It might be that. I don't like the word might, but it might be that. Okay. I think I get that. So let me try a different one. Let me try a different one. Let's try find a nice. See, where's chlorine again? 35%. So we just need to find one with another. Here we go. Here we go. Here we go. Let's get some of that molybdenum. 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 Yeah, something like that. All right. Let's try this bad boy then. Okay. So molybdenum. Okie dokie. So it has 95, 96, and 98. Whoops. And we're going to be multiplying this by something, multiplying this by something, and multiplying by this by something. So let's go and get the abundance. And I bet this should have this. So if I type in abundance, there is no way this big ass website does not have that. Hmm. Supply risk. So if I put in abundance of molybdenum, isotopes, natural abundance. Aha. 95, no abundance. Oh, here it is, yeah. So it's 30. 30. What does this say? Normal proportion. A mole fraction. What is a mole fraction? A mole fraction or molar fraction is defined as a unit of the amount of a constituent expressed in moles. The mole fraction is equal to the amount of constituent in moles. Total amount of all constituents in moles. Okay, cool, fine. I think this is what this means. Like because there's 30, 60, 90. I mean it can't be right. And yet I'm gonna go for it. So this is gonna be 96. It's gonna be 30. And this one is 98. This one's got, oh, you see, this one's got 80. I don't think that is right, yeah, because this is going to be percentage. Natural abundance refers to the abundance of isotopes of a chemical element as naturally found on a planet. The relative atomic mass of these isotopes is the atomic weight listed for the element in the periodic table. That's when an isotope varies from planet to planet. Yeah. Natural abundance is a mole fraction. Huh, that's annoying. Well, convert mole fraction to percentage. Oh, okay, so it is just that. Alright, that's awesome. That's really good to know, actually. So it's going to be, oh yeah, that's great. Yes, 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 yes. Sweet. Let's do that then. This is sweet. So we got, yeah, this times 3, times 100. 15.873. 15.873. And this one is 96. It's going to be that. 16.673. And 98 is 2. Wait. 24.292. I better do these as times, to be honest, because that's confusing me. Divided by, what we got here, 15.873 plus 16.673 plus 24.292, 56.838. So the output is going to be 95 times 15.873 sure, plus 96 times 16.673 plus 98 times 24.292 divided by 56.838. Yeah, okay. And I think that's because the rest needs to be taken into account. But let me check what we got here. Cast number. That is not right. And let's just add the rest. So it's going to be, yeah, let's plug these into Python actually. Python, this, sure. Nice, thanks. 1 plus 2, because I don't know if this works yet, so I just need to make sure I can run this. Run debug. Desktop. Work.py. Are you working? Oh, it does work. Cool. How did I do that then? So do I just do F5, right? Okay, cool, I like it. Let's do it. Let's do it. So we got relative mass 1 is going to be equal to, oh, see, I've got loads of them to do. Let me try a different thing. I want to see if I've got it right, but that's got so much. Hydrogen. Yeah, why not? Sounds good. Awesome. Okay, well, that helps. So we'll do mass 1 is 1 and mass 2 equals 2. And then we've got abundance M1 equals what? Isotopes of hydrogen. How many? Ha! 2. Alright, this is good, this is good, this is good. Range of variation. AM2 equals that. Then it's going to be M1 times AM1 plus if M2 times AM2 divided by AM1 plus AM1 plus AM2 print, oh, well, output equals that, print output. Let's go. That didn't work. It's going to be basically 1 times 99 and then 2 times some point. I don't know what this 6 is. Then they got the output is going to be the equation. So the output is 100, but that is not right. I've done something silly. Mass number 1 times abundance. The mass number 1 is it's 1 and 2. So if I go to the chlorine again, 35 and 37, 1 and 2. Yeah. So, oh, no, that's right. M2 is that times 100. And I did this from here, isotopes of hydrogen, and the moles was multiplied by 100. So we're going to have, I mean, why not? We're going to have that. Plus this. Yeah. So AM1 is going to be 99 plus 2 divided by 100, roughly. That was the equation, right? Yeah. I must be a complete idiot. I must be a complete idiot. There are 2 of them. Total abundance. It's almost 100%. A equals that, B equals A plus B divided by, yep, A plus B is going to be what? 99.974. A plus B is 4, so C divided by, it should be 1, right? What am I doing wrong? Oh, you fucker. Oh, jeez Louise. Unbelievable. Unfucking believable. Oh my god. Oh. Shit. God damn it, man. Wow. Well, there you go. Welcome to 10:51 session. Oh my god. Okay, well, I have to say I'm kind of interested now in the MO one because I would imagine I'm going to be the same, right. These are the main isotopes, so I'm gonna have to count these up. Um, oh, that is so annoying. Oh. So we're gonna have isotopes. Isotopes equals an array. Once again, I'm still new to Python, so we're gonna have 92 and 92 and 14.65. Sine. Synthetic rays is a radionuclide. It's not found in nature. Oh, oh wow. Synthetic radioisotope is a radionuclide that is not found in nature. No natural process or mechanism exists with which produces it, which is so unstable that it decays away in a very short period of time. Examples include technetium, 95 promethium. Many of these are found in nature, found in and harvested from spent nuclear fuel assemblies. Some manufacturing particle accelerators. Ha! So cool. Alright, let's get back on it. Now, okay, so we don't need to include that one. So we'll just take that off. 2, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5. Oops. 6, 7. Alright, let's do this. 94, 95, 96, 97, 98, and 100. And this is this. Oh god. Do this better. We can do better. 9.919, 20.87, 15.87, 16.67, 958, 24.29. Yes, sir. And that. So for how do we do a for each loop in Python? I'm guessing it's a range, isn't it? Let's see. Python for in. Okay, fair enough. Ah, for in. For isotope in isotopes. And we're going to do isotope 0 times isotope. Not that it matters. Running tally equals 0. Running tally plus equals. Oh, can you do plus equals? I don't think you can. I don't think you could do that. Python plus equals. Maybe you can. Internal add. Okay, cool. Fair enough. Then it's going to be running tally sum of numerator, sum of denominator equals 0 for isotope part in isotopes. Oh my god, just copy and paste. Jesus Christ. And then output equals sum of numerator divided by yes, running tally sum of denominator. It's going to be sum of numerator here, and I just want to do this sum of denominator there, and we're going to print this bad boy. Yes, 96.07. Let me just double check this. So we've got a collection of these do-raggies. Yep, and yep. And we got 100, 98, 97, 96, 95, 94, 92. Alright. Yep. And then we are summing them all to... yeah. Well, I think that works anyway. Yeah, it should be. It should be fine. So we're going to multiply them together. Yeah. Then we're going to plus them together. Alright, so if I did a print of sum of numerator, and then comment the rest out, should get a pretty thank you, Python. Thought I could do that. Oh, you can do that. Let's see. It's string, isn't it? Yeah. Oh, really? Do I have to do that? String? Is it string? Str? Convert int to convert float to string in Python. Excuse me. String, it is that. That's right. Why is it not like that? Oh. No, that is the list and we're getting the value back, yeah. I think so, yeah. What is it saying? Create a new string. Yeah, what's the error though? Error defaults to strict. Create a new string object from the given object. If encoding or errors is specified, then the object must expose a data buffer that will be decoded using the... like that? Let me actually read this error. Oh, so it was that. So you have to declare it in memory first. That's weird. I didn't know that. No, you don't. Oh, where the fuck's the error gone now? Ah, oh, stupid visual code. Right, so that is a big number. Cool. So then we've got this stuff. Sum of denominator 0.0. Isotope part in isotopes. Great, so we're going to cycle around those. And then we're going to sum of denominator plus or equal to 1s. So this should, let's see if this busts out now. String like this, yep, and like that. What we got? No. What? What do you mean this is commented out? Do I have to do that? What does this actually say? It says, restart video go to apply latest update. You have Windows Update Store. Do you want to install the recommended extensions for it? Sure. Later. Cool, great. Good for you. Save that. Unexpected end of file. Wait. Oh my god. Let's try this again. I am confused. It says in run modulus main, run code, run file and get compile file, unexpected end of file while passing. Okay, fine. Python application boilerplate. There might be something I need to do. What is it? Ah, okay, yeah. Might be that. Actually not sure. Def main. It might be this, it might be this, it might be this. Oh, how strange. What am I doing here? What am I doing wrong? What is this now? Invalid syntax. If name equals main, then do this. Test Python code. Oh, I don't want to be doing this. This is ridiculous. Run Python online. Great. What do you say? Oh, so this one's only got that. Yeah, I don't think I need that. It's just this, right? That's all I want. That's all we want. Run. Unexpected end of file while passing. Print. Oh, you fucking idiot. Right, okay, right, yeah, it's late. 99.9. So that is a sum of all parts. Great, that makes sense. And then we want to have the output. So it's going to be so the output is equal to the sum of the numerator divided by the sum of the denominator. Sum of yes, yes, and yes. Right. 96. So this is going to be, what was that again? Molly B. Denham. Its standard atomic weight is 95.95. That's interesting. So I wonder where I went wrong with that. I guess some of this. Unless it is this. 0, it's going to be 93, and then 99, like so. It might be that. Ah, sure. I wonder. Yeah, because that's times 0, isn't it? Yeah. Uh, hmm. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Why is that 95.95? That's interesting. Alright, well, I don't think I'm doing this right if I'm not getting the same answer. Standard atomic weight. Oh. What was this again? Isotope of MO. MO, where are you? E. Where is it? MO. 95.95. Key isotopes. So if I were to just do those key isotopes, what happens? I wonder. I think we already did this, didn't we? So 96.57. I'm one out. I'm about one out. This is annoying. I'd like to come back to this, I think. That is interesting. That is very interesting. I'm not sure I understand it. Plus equals. That makes sense. This is a float. List of integers. I don't know if this makes a difference, but I'm not sure I want to leave it out. There's some rounding. Ah, you see? No. Okay, that's the same. Yeah. Oh, you probably can't see any of this. I'm so sorry. But yeah, I'm a bit confused, to be honest, because the calculation is for the relative atomic mass. I'm plopping the mass numbers in, and I'm multiplying by the abundance I've been given, and I've got the total abundance. Not sure what's wrong there. A compound is 2 or more elements chemically combined. The table below shows in common compounds. It's useful to know that mono means 1 and di means 2. Carbon monoxide has 1 atom of oxygen, carbon dioxide has 2. Yeah, okay, right. So that's atomic structure. Structured CCEA, what does that mean? This might be good. What is CCEA? Okay. I think that's fine. So I think what I'm going to do is I'm going to do this tomorrow as well, so I don't forget all this stuff because I really want to make progress on um, understanding the structures and stuff. Um, like we said before, knowing how the covalent, how the where the where the electrons are in the energy structure, and then finding out that would help me understand how covalent bonds are asserting forces on each other, whatever forces they may be. Um, that was good to know. I think I actually quite enjoyed that as well. It was a nice little introduction back into it. So, okay, cool. So I'm going to leave it there. How much time have I had on here? An hour and a half. That's not too bad. So I shall speak to you another time. Ciao for now.